This is a massive utility-scale battery energy storage facility. These installations are designed to deliver megawatts of steady power to the grid. But occasionally, a system like this shuts down prematurely, despite sensors indicating the modules still hold a massive amount of charge. The central power inverters read the total voltage of the pack and declare it entirely depleted. Yet, if you calculate the actual energy that went into the system versus what came out, there is a severe discrepancy. Thousands of watt-hours are still trapped inside. To understand why this happens, look at how the cells are wired. This diagram shows a simplified series string. In a series connection, the charging process must stop completely the moment a single cell reaches its maximum voltage limit. Even if the other cells are only half full, the entire system is forced to halt. The exact same bottleneck happens in reverse. During discharge, that weak cell rapidly empties. Once it hits its lowest safe cutoff point, it shuts down the pack. The perfectly healthy surrounding cells never get to fully empty, leaving a large gap of stranded energy that you can never access. If you build a pack with factory-new grade A cells, the capacity difference between them is incredibly tight, typically 0.5%. But if you construct a pack with refurbished lots, the capacity spread between cells can swing by as much as 25%. If the battery management system fails to catch that weak cell hitting its limit early, it continues taking current. It gets overcharged, internal temperatures spike, and it swells, venting thick smoke as it enters a state of thermal runaway. When a large battery array catches fire due to imbalance, it is usually a process failure in how the cells were graded and matched, rather than a flaw in the lithium-ion chemistry itself. To safely build a module from second-life batteries, every single unit must be filtered using two vital signs: total capacity and internal resistance, or IR. This scale shows typical internal resistance benchmarks. Standard 18650 cylindrical cells sit at roughly 25 milliohms, while premium 21700 formats drop to 13 milliohms. But heavy-duty prismatic cells, like the massive 314 amp-hour blocks used in utility storage, operate on an entirely different level, testing near 0.2 milliohms. If you wire cells with mismatched resistance in parallel, they share electrical current unevenly. The cells with higher resistance absorb more physical strain, causing localized heating that damages the internal components. Internal resistance dictates how a cell behaves under load. It drives premature aging and ultimately creates the weak links that shut down your entire array. Because manual pack assembly carries high risk, builders follow a strict diagnostic pipeline for second-life cells. The very first step is to check resting voltage. If a cell drops below 2.5 volts, internal copper may have already begun to dissolve, sending it straight to the recycling bin. Next is an AC impedance test to measure that internal resistance. A 30 to 50% rise over the baseline for that cell format triggers a warning. If the resistance has doubled, the cell is rejected. Then comes the true capacity test. Cells holding less than 80% of their original rating are discarded. You have to use a full charge-discharge cycle to measure this, because high internal resistance artificially inflates the numbers on a charge-only test. The surviving cells are sorted into tightly grouped buckets. To build a reliable 72-volt pack out of 21700s, every cell needs to fall within a 1% capacity band, meaning you only use units testing between 4400 and 4500 milliamp hours. You never mix bands. Building strictly from a perfectly matched bucket prevents a rogue weak cell from sneaking in and dragging the finished module into an early shutdown. Even if you start with perfectly matched cells, micro variations in manufacturing will eventually cause them to drift out of alignment over thousands of charge cycles. Temperature is the most critical variable here. If poor airflow means a single cell runs a few degrees hotter than its neighbors, its internal resistance drops, its electrical characteristics shift, and it ages faster. The industry standard defense against this drift is passive balancing. As the pack charges, the battery management system bleeds excess capacity from the highest cells by running the current through a resistor, shutting it as heat. This wastes energy. And worse, it doesn't solve the discharge problem. When the pack is draining, passive balancing can't pull energy from strong cells to support weak ones, leaving the system hostage to the weakest cell's bottom limit. An active balancing system takes a different route. Instead of turning excess energy into heat, the hardware uses components like flyback converters to actively shuttle charge out of the strongest cells and inject it directly into the weakest ones, leveling the pack in real time. To verify this active system is actually keeping everything aligned, completed modules go through 4 to 5 full aging cycles to prove the balance holds up under continuous physical load. By strictly filtering out high internal resistance and deploying active balancing hardware to handle inevitable drift, builders can string together chaotic second-life batteries and produce highly reliable power storage.